We'll take a look at a reaction of a cyclic anhydride with an amine. The cyclic reactions or reactions that involve cyclic starting materials can be tricky because having that functional group in the ring means you typically have to cope with a ring opening in addition to the condensation reaction. We identify this as an anhydride because we have a pair of carbonyls flanking an oxygen. And those, of course, are electrophilic. We're reacting that with an amine, which is a good nucleophile. And we'll remember that anhydride is a reactive carboxylic acid derivative. We react a carboxylic acid derivative with an amine. We're going to make an amide, and we're going to make the amide at one of our carbonyl carbons. We could just pick this one arbitrarily. And that the other side will serve as a leaving group. So if we think in terms of that, let's color code our amine so that we can see which piece more clearly comes from where. We're going to end up with, and we'll draw that part of the ring exaggeratedly large so that we can more clearly see what's happening. We're going to end up making an amide, so we'll put the carbonyl this direction so that it's a little easier to see. And remember, this is our carbonyl carbon that we chose to react. And then we're going to connect that to our nitrogen. Now we're in technically neutral conditions, but amines are weakly basic. And so we do want to show the carboxylic acid in its anionic carboxylate state. And that means it needs to be paired off with something positive. And part of the reason we use an excess of the amine is that we can use it as the cation to react with the carboxylic acid. It also is going to be, we need a second equivalent to scavenge the hydrogen off the amide when it initially reacts. And so note that although this is technically a neutral mechanism, that we do still want to pay attention to the protonation state of the product. We take a quick look at that mechanism. We're going to use our amine as our nucleophile. Nucleophiles are electron donors, so we attach to the carbonyl, break the pi bond. We're doing a carboxylic acid derivative, which is an acyl substitution. So we're going to have a second key step here of reforming the pi bond and kicking out the leaving group. But initially, at least, we'll get our tetrahedral intermediate. Notice this other carbonyl is simply part of the leaving group. And so we're not doing anything specific with it. We'll just draw the nitrogen in black here since we pretty clear where those carbons are coming from. Now, because we have two hydrogens on the nitrogen to start with, now we have 4 bonds. We have a positive charge on that nitrogen. Again, we got a plus minus. We're in technically neutral or weakly basic conditions. So we're not in strong base, so we don't have to worry about not making O minuses and O pluses, and the same thing with nitrogens. So we can go straight to our reform carbonyl kick out leaving group step. Now, notice we didn't bother to deprotonate the amine here. We can wait until we have formed our anion to take care of that. Do notice that the leaving group was our carboxylate, which is a good leaving group because it's relatively stable. And at this point, I'll turn this nitrogen around. Well, no, we'll leave it. So we've reformed our carbonyl, but we still have this positive charge on the nitrogen. We could certainly envision the carboxylic acid or carboxylate picking it up, but because we've done this reaction in an amine, which is actually more basic than the carboxylate, then we're going to use it instead. So we'll have a second equivalent of that amine coming in, pick up that extra hydrogen from the amide. Now an amide, right, an amine can be protonated. Amides are not going to be protonated except under extremely acidic conditions. So this needs to lose its extra hydrogen. That gives us our product, which has an amide functional group on one side, carboxylate as the ammonium salt on the other side. If we wanted, by the way, the neutral product, we could have added a second step with a mild acid workup. That would give us our carboxylic acid. Notice then we've got 1, 2, 3 carbons. So 1, 2, 3 carbons. Then our carbonyl that's part of our amide or our amide. Now again, those are not basic. So even under an acid wash, they're not going to pick up a hydrogen.